Still here, honestly, a talk on Lambdas, last thing on a Friday. You're hardcore. I mean, you have my respect. You will have my slides in a minute, but you have my respect to begin with. Okay, so let's talk about Lambdas. This is a phrase that's been used a lot by programmers, language designers, and so on. And really what I want to do is I want to get inside this and say, well, okay, so what is this thing people keep talking about? Let's talk about origin stories, okay? This is basically the way that Hollywood works. You've had all the Lambda features released in your languages, now it's the origin story, okay? That we've released that. How do we monetize more Lambdas, okay? This is what we're going to talk about. And to understand a little bit more about what's going on, I mean, I've got to admit, it's a nice letter. It's one of the most pleasing letters to write, actually. But there's this thing. It has a number of associations. Amazon completely jumped on some crazy bandwagon. Oh, we're going to call this thing that's nothing to do or even remotely like functions and lambdas, we're going to call it Lambda. That'll confuse everybody, because it's kind of like functions, sort of. Yeah, RPCs. Done differently, right? So, yeah, it's nothing to do with that. No, it's not to do with half-life, which borrowed it from the idea of the decay constant in physics, where it's also used as a wavelength. Physicists like to recycle their letters quite a lot. They don't use namespaces. And then there's calculus, and that's the one that we're kind of interested in. Now, this all came out of the work of Alonzo Church, and he published this paper in 1936. So that's kind of the moment of inception, except actually it isn't. He published a previous paper in 1932, which I have not been able to get my hands on, even via the interwebs. But this is the kind of the basic reference point. He did some fixes in 1935, did some stuff. And he wasn't interested in what we are interested in. He was interested in computability, but in the same way that Turing was. Is something computable, as opposed to how do I actually write a program? And he was exploring this, an unsolvable problem of elementary number theory. This was really just the exploration of the Entscheidungs problem, which is related to the halting problem. And in the same year, Turing came out with a similar proof that was then shown to be compatible, but using Turing machines, and these were shown to be actually equivalent. And so but as a by-the-by, in this paper, which I am not trained as a mathematician, so I kind of reach a sort of sheer G-force acceleration after a couple of pages, going, I'm not really totally sure I'm with you here on this one. There's a lot of assumed context. But he just tosses in lambda calculus. It's just a very casual thing. But it's also interesting, because this is the 1930s. And this is a period at which, it's worth understanding, where a number of certainties about the future were starting to be torn down. And I'm not making political references just yet, but I could easily do that. There was this idea at the end of the 19th century that we had, everything was knowable. Knowability, everything could be complete, maths could be consistent and complete, and all of this started tumbling down in the 1920s, the end of the 1920s, thanks to Kurt Gödel and the incompleteness theorem. We discovered the halting problem. There's a whole series of things. By the way, relativity came along to just say, oh yes, black holes. That was a nice side effect of relativity, which was 1915, when Einstein first presented it, properly published in 1916. And then other people started working through the equations and going, wait a minute, there's a really weird thing here, what we now call a black hole. A boundary of knowability. And it turns out that the 1920s and 1930s came along and tore down this edifice of like everything is knowable. Oh, by the way, quantum mechanics. It's just like, oh. So that was the stage, which ultimately gives us this idea of what we have is rigidly defined areas of doubt and uncertainty, that certain things cannot be known and are unknowable. But it turns out that lambdas they are knowable. They were left as a kind of theoretical thing, something of interest, pretty much until the end of the 1950s, when McCarthy and others started designing Lisp. The first implementation of Lisp was 1960, and it was pretty much based on lambda calculus. And lambdas were a feature in the language. And this was kind of like the first time this was just like, right, made its way in to computing. And these days, it's kind of like, I just did some Googling around the other day, and there's this Ruby tutorial. You may have heard of Lambdas before. Perhaps you've used them in other languages. It's now got to that point where we kind of assume that people have heard of them. There's a strong assumption. Despite the fancy name, I don't know, picking a letter is not particularly fancy. I mean, dominant programming languages through history. C. Well, that's a fancy name. No, it's just because it chooses a letter from a different alphabet. It's like that. A lambda is just a function, peculiarly without a name. And do you know what this actually means in terms of solving deep, significant problems? It means that this classic quote from Phil Carlton, okay, it turns out, 2 hard things in computer science, cache and validation and naming things. We're done. We've just reduced it. If lambdas mean you never have to worry about naming things. And cache and validation, if you're doing functional programming, it turns out there's no such thing as invalidation because that's a process with a side effect. Nothing happens in functional programming. It's so pure that even if you unplug your computer, your functional programs will still run. Oh, wait a minute, that doesn't work. Yeah, they're riddled with side effects. That's all that makes it. All of this stuff is an illusion, okay? Functional programming is an illusion. Every paradigm is an illusion. But we can do that and basically say, right, we're done, we can go home. There are no more problems. Because it's also cache and validation is not relevant to this talk either. So what was Church saying? Oh, he said, right, okay, so we select a particular list of symbols consisting of the symbols, open, close curly, open, close parentheses, lambda, square brackets, and an innumerably infinite set of symbols, A, B, C, etc., to be called variables. And we define the word formula to mean any finite sequence of symbols out of this list. Now, this is a shift from the way that people have, and within the paper, he also uses traditional function notation from a mathematical perspective. And there's this very simple but subtle idea that a function is a name, and there is a formula. And the function begins with a name. And what we're doing is we're basically saying, you know what, if you do have a name, it's just kind of like on the side. And that's a convenience, but it's not a fundamental idea. And we're going to shift this, and we're going to treat these things as first class, that there are only values. And that's the thing, in lambda calculus, there are only values that are lambdas. That will turn out to be interesting a little bit later. And so here we have a very simple lambda expression. And I'm going to use this to demonstrate basically the 3 rules of what makes a lambda a lambda. The first thing is a variable. It seems trivial, we take these for granted, but this is the basic idea that you have something that can hold a value. That value must be a lambda in pure lambda calculus, but you have a variable. We'll see in a moment there's 2 kinds of variables. The next thing is you have abstraction, function abstraction, where what you're doing is saying that this variable is bound within this context over an expression, y of x. And to be precise, it's y applied to x. And y is a lambda being applied to a value. So application. So it turns out these are the 3 things. If you've got these, this is fundamental. You have variables, you have function abstraction, you have application. If you've got that, that's it. Now, a couple of other things. That thing f that I had before, that's an abbreviation. It's not formally part of lambda calculus, but it turns out it gets quite boring when you have to write everything out longhand. Although he wasn't saying don't repeat yourself, that's what he meant. These are convenience, but this is really important because it means, just as an aside, not a topic I'm going to cover here, it means that is simply a stand-in for that. Because it's not a definition, because it is an abbreviation, it basically means that you cannot refer to f on the right-hand side, which means that lambda calculus does not support recursion, which is going to upset a lot of people who are just like, wait a minute, isn't that all of functional programming? There's a whole bunch of things called fixed-point combinators that get kind of interesting, and maybe in an extended version of this talk I'll explore that. But these are just abbreviations. They turn out to be surprisingly convenient. The next thing is to look at the kinds of variable that we have. Bound variables, that comes in as a parameter. That's your classic parameter. And free variables. That means that that's defined somewhere else. And that somewhere else is kind of an interesting thing. We'll come to that in a moment. So let's just look at something fairly simple, and what I'm going to do is I'm going to introduce something beyond lambda calculus, that little time symbol, strictly speaking, the purest form. purest form of lambda calculus has nothing else to it. I just showed you the whole thing. And it's got a few reduction rules, and that's it. But for convenience, obviously, it's just like, yeah, let's throw some mathematical stuff in. Let's make life a little bit easier. So we take our standard definition of what is square, and we do something like this. So therefore, this is an abbreviation. I apply that. Guess what? Innumerably infinite symbols. I'm not saying Alonzo Church invented emoji, but he accommodated it. He didn't say there's a bound set. He said no. And that means that that's a cross product. I know, that's terrible. It does not get better than that. In fact, we can do the whole thing. This is great. So I can now get square. He said innumerably infinite. I'm going to take him at his word. And so we can apply that to 7, or we can do that, or we can write the whole format. So there we see in its purest form, we've used simple types, and we've got a simple application. We're very strict about things like parentheses as programmers, about where they go. That's not the case with mathematicians. It's just like, yeah, I'm feeling, he actually switches through the paper how he does function application. F parens of x or F space x. He says parentheses are just there to make things a little bit more visible. I'd just love to see compilers do that. It's just like, yeah, I think I understood that. I feel I understood that. I'm going to go with this. So that's the kind of thing you can get away with in a paper. Now, let's make this real. JavaScript doesn't get more real than that. So traditional JavaScript, we are brought up with the idea of thinking we name functions. A function has a name. That is your starting point. But actually, we could do it like this. Now, there's an interesting point about, and one of the reasons I've chosen JavaScript here is not simply that it is broadly accessible, but Brendan Eich, when he developed it in the mid-90s, the tale goes that it took him 2 weeks to do. And there's half a dozen jokes that hinge around the fact we're not quite sure what he was doing in the second week. But actually, what he wanted to do was implement a version of Scheme. I will come to Scheme in a moment. But people said, nobody's going to buy that syntax. You've got to use familiar syntax. So basically, it's kind of an interesting mashup. He said, OK, right, I'm going to use C-style syntax. I'm going to use lambdas. I'm going to use ideas from Scheme. So it's a list-based language. I'm going to use ideas from that. And I don't really want any of that complex objects. So I'm going to use a really simple prototypical model of objects and go with that. But from the very beginning, it was always in there. Now, strictly speaking, some people get very fussy and say, well, no, that's not really a lambda because it's just a function without a name. It turns out that these are not necessarily equivalent, but some computer scientists get very upset about them being regarded as equivalent. So I'm going to treat them as equivalent. So anyway, what we get is ECMAScript 6 comes along and says, we've got this arrow form. We're going to make life even easier. And we've got even more abbreviations. And actually, if you've only got a single expression, then, yeah, life gets very easy. So this is all good. This works out really well. Let's go back to that Ruby tutorial. They're anonymous, little functional spies sneaking into the rest of your code. I don't like the sound of that. I mean, I've already got Facebook to worry about, and now you're telling me my lambdas are going to gang up on me. But we have a point here about the way that people perceive them. Not the spy bit, the functional bit. People immediately associate lambdas. They say, oh, right, lambdas, that must mean functional programming. So 2014, Java gets lambdas. Lots of people going like, I am now functional programming. It's Java, mate. You're not functional programming. Really. Yeah, but I'm using lambdas, and they're like totally functional. It's just like, OK, let's take things down a bit. Let's reduce our excitement here. Excel, interestingly enough, which does not have lambdas, although it's been suggested. I don't know. I think spreadsheets already have enough bugs in them. I'm not quite sure that the public's ready for lambdas. But Simon Peyton-Jones, Mr. Haskell, basically made this observation: Excel is the world's most popular functional language. Functional means a number of different things to different people at different times. They start from different positions. Some people say, right, functional programming is rooted in this. For me, it is lambda calculus. For other people, oh, no, it's to do with Hindley-Milner type systems. That is functional programming to me. It's kind of like everybody has their own personal version of this. But I want to go back to Lisp, because this is the one that was kind of interesting. This is the one that triggered a number of ideas. And there's a certain beauty and elegance to the original Lisp. This is the manual for the original Lisp. I have a copy of it at home. You can find a PDF online. It's quite brilliantly written, actually. It was written in the early 60s. Lisp 1.5, there was supposed to be a Lisp 2, there never was. The syntax, they were going to tidy up the syntax and make it less list-oriented, but actually it turns out the syntax, the merging between data and code, treating them as the same, was not a stepping stone idea, it was actually a really big idea. And they would kind of think, oh, we're going to change the syntax, and it's just like, no, you know what, there's something really good here. But we use Lisp generally to mean anything that kind of looks like Lisp. There's a monster called Common Lisp, which I've had to grapple with in the past a couple of times. A number of people are familiar with the Emacs Lisp, eLisp. There's lots of different flavors. All of them are significantly larger than this. But there's a certain elegance to it. And I've described to people, you need to get infatuated with this. I don't think I've ever been paid commercially to write Lisp code, although I think I managed to sneak some stuff that was Lisp-ish in a couple of places. But there is an elegance to the thinking. There's something really clean and simple. Alan Kay of Smalltalk fame, when he saw part of some of the ideas in this book, he said basically that this page, this is the laws of physics, or Maxwell's equations to be precise, for programming, or languages in particular. It was really inspired, and that inspired a lot of Smalltalk. I'll come back to that a little bit later. And so we can always get carried away with this. And, you know, XKCD. Last night I drifted off while reading a Lisp book. Suddenly I was bathed in a suffusion of blue. I noticed the coincidence that actually, I don't think Randall Munroe intended it, but that is the blue of the original book, and there it is. You know, nice coincidence. Suddenly I was bathed in a suffusion of blue. At once, just like they said, I felt a great enlightenment. I saw a naked structure of Lisp code unfold before me. The patterns and meta-patterns of dance, syntax fade, and I swam in the purity of quantified conception of ideas manifest. 2001 reference there, which, if you know Lisp, is hilarious. If you don't worry about it. Truly, this was the language from which the gods wrought the universe. No, it's not. It's not? I mean, ostensibly, yes. Honestly, we hacked most of it together with Perl. There is a certain pragmatism to the way that things come out. And as for those regexes for quantum mechanics, you're on your own, kid. But that does bring a rather interesting point. Lambdas really have got everywhere. To try and claim them for your paradigm is not really going to work out. I'm not going to do anything with Perl. I have a kind of there's a bit of me that won't let me do Perl. You know, it's kind of like Sith speech. I just can't do it. I'm not allowed to do it. Perl is executable line noise. It's one of my least favorite languages, and I like languages. But PowerShell, let's use a scripting language. Here's PowerShell, here's a Lambda. That's the square. That's quite nice. Actually, PowerShell is a surprisingly good and well thought out language. And if I want to give it a name, I can bind it to a name. I can apply it. I've got a really simple application syntax. There it is. It's very direct, and that's it. So I've got all these options. I can even do it. This is now you know it's a proper Lambda because you can just take that, and you don't need the name with which to execute it. And that's that substitutability, that freedom. The idea is that the name is simply an abbreviation for something else. If you've got that, this is a really good thing. Then let's also, let's go back to the 60s again. Algol 68, possibly the most influential language you've never used. All of those you using languages where there's the keyword int, yes, that came from Algol. Prior to that, all language design involved using the word integer. Int, character, char. That's where it all comes from. Void, that came from Algol. There's a load of stuff. It really is. At the time, it was seen as this monstrously huge language that nobody would ever be able to implement. Honestly, I've got a copy of the language report. It's kind of really quite small compared to modern languages. This is not complex. But, guess what? One of the things I love about Algol is it is unforgivingly procedural. It does the procedural paradigm properly. Algorithmic language, there it is. It does the procedural paradigm. It's committed to the procedural paradigm, so committed that you can have unnamed procedures. That's how committed it is. Yeah? They were a standard feature. It's a standard concept. Okay, so I can go ahead and I can bind this simple anonymous procedure square. So I just want to remind you, 1968, okay? If you got really, because you've got all the other languages going around. It's like, yeah, Java's going like 2014. We got Lambdas, and everybody else behind it is going like, hi, C++ here. That was 2011 for us, and C# sitting there going like, shh, come on, we're in the 2000s. JavaScript in the background going like, yeah, mid-90s. Lisp is kind of like, yeah, 1960, but somewhere in there, in the 1960s, this was kind of a normal feature of language design. COBOL did not have it, but a lot of other languages had this ability to have this kind of procedural abstraction freely available. So I've got to declare it as it's a language that has a concept of types, doesn't do type deduction, so I do have to go ahead and declare these things. But I can apply it. I can also, as we expect with application, I can just apply it freely. I can just take that expression and apply it to 7, and it will give me the square of that. So it's a little bit much to try and claim I've just shown you scripting and procedural. I mean, it's not that. Oh my goodness, Lambdas in Ruby are also objects, just like everything else. Okay, we are not done with this paradigm, apparently. So pick this one up from a discussion group on which years ago there was a discussion I dug out with Guy Steele and a number of other people. Guy Steele was, he's a kind of languages expert, had a hand in a number of languages, worked for Sun, but prior to that, he's been involved in a variety of languages, most notably Scheme in the 1970s. Really nice bloke, very, very knowledgeable, but this was kind of a response, and somebody was kind of describing it. The venerable master Quagnar was walking with his student Anton, hoping to prompt the master into discussion. Anton said, "Master, I've heard that objects are a very good thing. Is this true?" Quagnar looked pityingly at his student and replied, "Foolish pupil, objects are merely a poor man's closures." So closure is a term that gets thrown around a bit. And actually, Wikipedia has one of the best definitions. I dug around, and I don't always like to rely on Wikipedia, except for the fact that sometimes they absolutely nail it, and it's a really good condensed tour of it. The concept of closures was developed in the 1960s. That's a hell of a decade. For the mechanical evaluation of expressions in the Lambda calculus. They were invented to solve this problem. How do we lift this stuff off the page and use things that we are familiar with now, scope, binding of variables, things like that. How do we do this? Peter Landon defined the term closure in 1964 as having an environment part and a control part. Now, what is interesting is I encountered closures. There are things called closures in a number of languages. And I encountered closures at one point in Borland's Pascal, their Delphi stuff. And I thought, these are not closures. They're just bound methods. I can't give you a chunk of code. I can simply say, here is an object, dot, here is a method, and I'm going to pass you that bound thing. And that's a very poor version of closure. But strictly speaking, it does kind of fit as having an environment part and a control part. It's just that you can't do much about it. It's just that you have a very restricted idea of what environment is and what control is, a pointer to a method, but it must be a named method that already exists. So that's very different to the Lambda idea, which is it doesn't have to have a name. In fact, we're not going to assume names. The environment part is the binding of the names. Now, importantly, these ideas become a little more popular for a number of reasons. John Moses credits Landon with introducing the term closure to refer to a Lambda expression whose open bindings, the free variables, have been closed by or bound in the lexical environment, resulting in a closed expression or closure. In other words, those free variables, we now have a regular concept like that freestanding Y, that refers to this. It's not totally freestanding. We have an idea of scope, if you like, and that gets passed through. This turns out to be quite an important idea, one that, again, we take very much for granted. But this does also allow you to, if you find yourself in one of those absolutely fascinatingly pointless debates, is a Lambda a closure or a closure a Lambda, there is now an answer. A closure is a Lambda that had free variables. If it has no free variables, in fact, so square, for example, is not a closure because it is fully self-contained. All of its variables are bound. It takes X, it only uses X, we're done. Okay? Now, the bit of history that is more important and interesting, this usage was subsequently adopted by Gerard Sussman and Guy Steele when they defined Scheme in 1975, a lexically scoped variant of Lisp, and from that point on, it became widespread. That was the kind of like the inception point for the popularity of the term. It started taking it out to other people. Now, that becomes interesting. Let us go back to Anton. Chastised, Anton took his leave from his master and returned to his cell, intent on studying closures. He carefully read the entire Lambda the Ultimate series. This is a series of papers by Guy Steele and colleagues that kind of showed how powerful lambdas were, written primarily in the 1970s, but that name has been taken and is used for a site that's dedicated to functional programming, Lambda the Ultimate. A series of papers and its cousins, and implemented a small scheme interpreter with a closure-based object system. Now, this book is sort of computer science classics, structural interpretation of computer programs. One of those books that it's kind of everybody eventually refers to, few people have read, has one of the dullest titles, but there's a lot of really interesting stuff in there. That was by Gerald Sussman, and partner in Harold Abelson. Interesting thing in here, actually as an aside, is the Maxwell's equations, as it were, for programming languages. This is the scheme interpreter written in Scheme, or the heart of the scheme interpreter written in Scheme. This is that's demonstrating something we would sometimes refer to as homoiconicity, the idea of a language representing itself. This is part of the same mind-bending stuff when you first hear about cross-compilers. You know, I remember coming across that, like, how can you write a C compiler in C? That doesn't make sense. Yeah, there's a couple of extra tricks you have to get in there, but the idea is let us write this one out and let us do this, let us describe the language in terms of itself, then translate that, and then you've got the kernel, and then you can kind of bootstrap everything from there. But it's a very profound idea because you can see it's very simple. It's a favorable font. It fits on one slide, and that is kind of everything that you need to make this stuff work. What is interesting is that Alan Kay did the same for Smalltalk. He wrote the basic idea of Smalltalk in Smalltalk. He did this kind of exact Lispish type of thing. And Smalltalk is all about closures and this idea. However, whenever people sort of always talk about purity, I just did it with Excel and functional programming. It turns out, this is a thing I discovered a few years ago. Dan Ingalls was somebody who worked with Alan Kay at Xerox PARC. Dan Ingalls implemented the first version of Smalltalk 72. Now, Smalltalk is a language, it's often touted as a very pure object-oriented language. Very few people use it now. Very few people have had hands-on with it. But its influence is quite marked. In fact, if you go and look at Ruby, a lot of that, Mats was inspired very heavily by ideas that he found in Smalltalk. But what is interesting is that Dan Ingalls took the Smalltalk version of this and implemented it at home using BASIC. It's kind of like, it's beautiful, elegant object, because it was this is the 1970s, time-sharing systems had just come in, and what else do you have available to you on a time-sharing system? You didn't really have high-powered compilers. He was busy working at home, and it turns out that BASIC was the only language available, so you make do with what you've got. Now, this is kind of interesting, because you can actually see there's a little bit here that says Lambda, and that's kind of, that's one of the more interesting bits. There we go. There, Lambda, make procedure, bind the environment, and do all the rest of it. That's all good. That turns out to be quite an important bit. In a paper published in the mid-70s, Sussman and Steele point out, they say, well, here's why we did this. We weren't just inventing languages for kicks. This work developed out of an initial attempt to understand the actorness of actors. Carl Hewitt had come up in the early 70s with this idea of computation, the actor model. And Carl Hewitt had some crazy ideas. I've read some of the original papers. I ended up doing my master's degree thesis was on actors. And I have to admit the Carl Hewitt stuff was the least accessible. And hence I understand the motivation. What is an actor? Is it an object? What actually is it? So they did what a number of people did in academia at that time, is if you don't understand something, let's build a language to understand it. Yeah? And this was a part of a series of languages. There was a kind of a culture in the AI community back then of naming your Lisp variants after something like, well, one of them was called Planner, another was called Mapper. This was supposed to be called Schema. You get the idea of what's going on. The problem is that there was a six character limit on file names. So schema less one, trim down, becomes scheme, hence the name scheme. This interpreter attempted to intermix the use of actors and Lisp Lambda expressions in a clean manner. Now, I saw a talk by Guy Steele in 2005, 2006. What was interesting is he talked about this. When it was completed, we discovered that actors and the Lambda expressions were identical in implementation. In other words, it turns out that that bit there that says Lambda, it turns out they had another bit, and they called them alpha expressions for actor. It turns out it was syntactically identical. This is the joy of having code that fits on one page. So they said, wait a minute, it's exactly the same except the names are different. But other than that, it's structurally similar. Wait a minute, boom, mind blown. Actors are Lambdas. It's like, wow, cool. So that's where it all comes from, but that was the motivation. So we've now just unified another paradigm with Lambdas. At this point, Kruknar has another walk with Anton, who attempts to impress his master by saying, Master, I had diligently studied the matter and now understand that objects are truly a poor man's closures. Kruknar responded by hitting Anton with his stick, saying, when will you learn? Closures are a poor man's object. At that moment, Anton became enlightened. There's this kind of duality here, and it's one that we kind of pick up. It's a rather nice paper from 2009, William Cook. It's based on revisiting a paper on data abstraction and polymorphism that was very influential in 1984. Luca Cardelli, Peter Wegner published it. And William Cook goes back to it. I don't know the number of points he makes, but one of my favorite is Lambda calculus was the first object-oriented language. By looking at a number of things related to polymorphism and so on. And we can actually see this if we look at, so this is Seven Mountains, just outside Las Vegas. As you can see, the data structure in use here is the stack. I'm going to be traditional with this. So, you know, here we have, this is, if you like, this is a kind of a functions as objects, sometimes called modules, but that's not, that terminology has fallen out of favor. But this is the purest object model that lives inside of JavaScript. There's quite a few object models that live inside of JavaScript and lots of different ways of getting them. But if you like, this is the one that most directly represents this idea of closure and pure data abstraction. And so what we see here is simply I've got the outer thing. I'm basically saying I've got a name that I'm going to associate. It's just an abbreviation. There's no cycles here. It's a Lambda. You call it, and then you will get a new thing, a new record or a new object that happens to have names accessible, depth, top, push, and pop. And each one of these is bound to a Lambda, each one of which is indeed a closure because it's referring to a local variable items. That items list is about as private as you can get. It's an array that is a local variable, and it's truly local. It's bound in with the scope. So it's not in the sense, there's not a keyword thing going on here. It's hidden because it's hidden. It's not hidden because it's inaccessible. That's a difference. In languages like C# and Java, if you say, oh yes, we've hidden this, no you haven't, I can see right there on the page. I can do reflection and I can see it right there. That field, it's there. You've just said you can't access it. I can perfectly well see it, but you just can't access it. Whereas here, it's just like, no, there is nothing. This is the bottom of the iceberg. So this takes us to another paradigm. And a lot of people associate structured programming with the idea of go-to-free programming. So this book was published in '72 based on work in the late 60s and early 70s. And in it, they make a really important point. One of the most powerful mechanisms for program structuring is the block and procedure concept. So I'm going to give you some code here that is based on a language based on Algol 60, predecessor of Algol 68. And what we're going to do is we're going to have an array of items, 1 to capacity. You couldn't have dynamically sized arrays. So 1 to capacity, or rather, you could not have dynamically allocated. You can capacity, as long as that's in an outer scope, we can allocate that on the stack. And it's got a reference to rocks, and we're going to keep account of how much of that capacity we've used. Just as a general point, you have a nil. There is a null reference here. This is the null reference that was borrowed from another language in the Algol family, Algol W. Tony Hoare kind of feels he is responsible for inventing null, which he calls a billion-dollar mistake. But this is where it comes from. And then we can actually we can go ahead and initialize that. And because it's a proper block-structured language, and this is the thing I think we've also forgotten what block-structured originally meant. It meant that you could put anything in a block. That means if you want to put a procedure in a block, you can put a procedure in a block. It's as simple as that. There's no idea of there's a top level and you can't define nested things. It turns out, curiously, that a number of languages are kind of caught up with this one a little bit late. So C# said, you know what, we're going to have these kind of like, you can have these kind of methods nested inside your methods. This idea is a very, very old one. But that idea, being able to offer operations, depth, top, push, and pop on that is interesting. So that's a block of code. That's your begin and end. That's your open and closing curly. A procedure which is capable of giving rise to block instances. Now, that's kind of interesting because, given especially as we're talking about stacks, the whole point here is that normally when you think about blocks, it's stack discipline. You enter a block, you get your variables, you do your work, you leave the block, and that's all gone. Okay? It's gone. There are no more variables, that's it. Some of those objects may live on thanks to the garbage collector, but that's done. There is a very simple idea here. What if it doesn't go away? What if the block is itself a thing? What if you return the block and say, look, I've got a block and it's got procedures in it and it's got variables, it's got state. Here, have this, you can use it. And that was the beginning of object orientation. The language in question, so here we go, which survive its call will be known as a class, and the instances will be known as objects of that class. And classes did not have to be named. They could be anonymous, just like lambdas. You could have unnamed classes. But I'll show you the named version. What I do is we take that, and then we just simply add that at the top. And we're done. And that's where, so this is Simula 67, the first object-oriented language. It was based on Algol 60. And it follows exactly that idea of why don't we take a block and then add the idea that the block doesn't go away when you've left it, it can become a thing that you can refer to. Wow, you can create a whole paradigm out of that. And again, the lambda-ness of that is pretty cool. We could, of course, use any notation we want. Do not laugh at notations, invent them. They are powerful. So Nobel laureate Richard Feynman made this observation. In fact, mathematics is, to a large extent, invention of better notations. So let's talk about that. Alonzo Church was asked, why did you choose Lambda? And there are a number of different origin stories. The one that is the most rational goes like this. You've got an abstraction. You basically want to say, I've got A. A is a bound variable. I want to show an abstraction with respect to that. And his original form was this. It was a caret. Okay, just got to put it. Note, by the way, this also means something I haven't said so far, and unstated. Lambdas can only take one parameter. Because if you look at that notation, it doesn't make sense to have two parameters. You can't do it. Lambdas can only take one thing and return another. And that was the idea. Problem is, and trust me, you get a lot of trouble trying to find an A circumflex. Just don't worry about your infinitely enumerable symbols. It's quite tough. If you're a typesetter in the 1930s, you go like, come on, mate, really, give us a break. What about that? There we go. That's the story that makes the most sense. Later in his life, Church gave other stories, which is, I liked it. Whim, that was it. Why not? Yeah? But I like that story because it also helps demonstrate some of the aspects of what Lambda is. So what did the other languages do? Well, they took Lambda and, some of them imaginatively called their Lambda abstraction Lambda. Okay, so this is what Lisp did, this is what Scheme did. If you work in Python, this is what Python does. Haskell kind of said, dude, that's so verbose. There we go. Everything you need to know. That is one of the most minimal notations out there. Clearly, you've got stuff like JavaScript, which came along and said, we're going to call it function. And then you get languages like Clojure, so a kind of a Lisp variant running on the JVM. It decided to call it FN because clearly, vowels, they're bad. So in some languages, you get func. In other languages, you get fun. Here, Now, what I consider this to be profoundly ironic. It basically means that Clojure has anonymous functions, but there is nothing in the language that is called a lambda. What is the logo for the language? A language that does not have anything called lambda. There you go. It's either ironic or deep or quite possibly both. We get C++. That's a great one. This is actually, you get a choice of whether you want to capture Clojure or not. So we get square brackets. Now, this gives some great syntax. This is a valid token sequence in C++. Okay? What it is this is a lambda that captures nothing, takes no arguments, and does nothing. And here's how you execute it. So this is kind of, so this does, this is silence of the lambdas, if you like. I told you they weren't going to get any better. So then we get other languages. We've got JavaScript, we've got C#, who say, we're going to go for this arrow notation. And then you've got some other folks, Groovy, and Java's like, no, we're going to be much more lightweight. See? That's much more lightweight. It's just like, yeah. But it's kind of interesting because here it is in Java. Here's the thing that does nothing. Well, I have an interesting question. How do I execute that? That's a Lambda expression in Java, but how do I execute it? That does nothing, but how do I execute it? And we have exactly the same problem in C#. How do I execute that? Here's a thing that does nothing. How do I execute that? And that's kind of an interesting one, because it actually opens up a number of issues. Because what is the type of the return? Well, in the original Lambda calculus, there was only one type. There are only lambdas, that's it. But we have grown used to languages that have a very particular vocabulary and set of concepts. The languages, most of the languages that I've described so far, are C-based languages, which have their origins in Algol. The syntax has shifted, but all of the ideas are there. And there's a fundamental idea in all of these languages. You have expressions. And all expressions have a type. Clearly, we can kind of say, well, the original Lambda, but what is the type of that expression in C#? What is the type of that expression in Java? These are C-related languages in terms of their concepts and vocabulary, but it turns out that we cannot name, actually it's not even in case we can't name it. It turns out that they don't actually have a type. They're not expressions in the conventional sense. The original Lambda calculus is often referred to as untyped. There's been a move recently. People have described unityped, which is kind of cool if you want to confuse your colleagues. If you're having one of those dynamic versus static type debates and you think it's getting away from you, just throw in new terminology. This is untyped. Oh, I think you'll find it's unityped. It's like the type of the web is the string. The type of the enterprise is the core dump. There's lots of different ideas of there is one true type. But yeah, shell scripts are historically unityped around string. They are stringly typed. But there is only lambdas. So this is kind of interesting. What do we do? Now, clearly having just untyped lambda calculus is annoying. And in fact, Church later developed a simple typed calculus, and a number of other people kind of assume that. It's just like, I want my convenience. I want to use lambdas as a vehicle in the context of other things. I don't want to have to build everything up from scratch. That's a little bit, banging my ones and zeros together. I haven't really moved to a very high level there. So we normally assume that there is a type system. But let's go and have a look at what languages do. If we go to Haskell, that is our square. In the shell, I can go ahead and ask, what's your type? And it will tell me. And it has a well-defined type. This works with classes of numbers and gives you a result that is of the same type. There you go. It has a type. The type is determined. In C#, C++, it has a type. You cannot name the type. The type is anonymous, but it has a type that can be deduced, and you can use it. It has a type that has certain syntax associated with it. If I go to Python, I can sit there and wrap that expression in type, and I will get an answer. It'll tell me, hey, this is a function. This is an object of class function. But if I go to C# and try and get type, this does not work out quite so well for me. Operator dot cannot be applied to operand of type lambda expression. That's it, no explanation. I'm sorry. Do not pass go. But why? You just can't do it. It's like, that's a bit frustrating. Well, tell you what, maybe I'll just put it into a variable. Yeah, same deal there. Again, no explanation. You just can't do it. Yeah, but why? No, I'm not telling you why. It turns out that that's one of the key distinctions. So this is the interesting thing. It turns out that's not a lambda. I mean, it's called a lambda, but it's not a lambda. You can call it what you want. You can call it Fred. I'm not going to argue with your choice of names there, but that is not a lambda expression because it doesn't support application. To get it to do anything, I have to do that. Now, technically speaking, based on everything I've just said, this is a lambda expression. That bit away from the type is not a lambda expression. So there are lambdas that aren't lambdas, and there are other things that we don't call lambdas that are lambdas. And, what about Java? Yeah, what about Java? It's slightly, well, at least we got to use normal function call or method call syntax here. And when we hit Java, it gets a bit messier because Java doesn't have this idea. It basically says you can't do any kind of, there's no abstractions for operator overloading or being able to hook into that in the language. This simply doesn't exist. And so there's a bit of a compatibility issue here. In fact, there's a bit of a consistency issue. That is not a lambda. If I want to execute it, I can't just put parens around it like a method, so it doesn't behave like a functional abstraction, the other functional abstractions in the language. It turns out there's a whole library of interfaces that I can use to wrap lambdas, and I can also apply my own, but those are not the type of the thing. They are things, in other words, the lambdas used to generate something, but I can then give it a type. And it's a big old mess. It's a big old mess. And that's just the basic variance. That's 1 and 2 parameters and deals with the fact that generics are not reified in the language. There's a lot of duplication here. So did they choose a consistent name? Given that we understand that normally how you call a functional abstraction is to use open parens, close parens. That is the one syntax to rule them all. So surely they must have chosen one name, one consistent name. No, they didn't. Some of them are called apply, some of them are called test, some of them are called accept, and some of them are called get. So there are 4 different names. Actually, it turns out there's 5, because if we want to do this one, there's run. Now, sometimes people say, well, yeah, we don't have enough information to deduce the types, and that's quite reasonable, because these expressions tend to be very light. A lot of deduction needs to go on. What's the return type? Well, we have to have a look. What are the parameter types? Well, we're going to have to look at the context. But I've just given you an expression that has no context. It's bound to nothing. It takes no arguments, returns nothing. It really is, if you're looking for a type, it's void void. So there's no deduction to be done here, but we have to jump through the hoops here. So yeah, it turns out that C# and Java do not support the third of the 3 things. So they are very useful, but they are not really strictly lambdas. Now, it may come as no surprise that Alonzo Church doesn't care about any of this, not simply because he is long since deceased, but this was not the problem he was trying to solve. It turns out the lambdas came out to be useful for other reasons, but his original motivation was something, well, it was to do with numbers, countable numbers. Innumerably infinite sequences of numbers, and do they have, well, can we find an end to things? Yeah, is there a finiteness to certain sequences of execution or not? This is a very simple question. It turns out it has ridiculously hard answers. So this observation, God must have forward slumped against a bulkhead and started to count to 10. He was desperately worried that one day sentient life forms would forget how to do this. Only by counting could humans demonstrate their independence of computers. So, of course, remember I just said, right back at the beginning, and I've kind of nudged it every now and then, if you do pure lambdas, there's no numbers, because there are only lambdas. How are you going to do arithmetic when you've got no numbers? Well, the answer is obvious. You invent them. Yeah? You create your own numbers. So we're going to start with nothing. And this is, in fact, curiously enough, Church did not need a 0 in his original paper, but here's a 0. And here is a lambda that takes 2 parameters, f and an x. X is itself actually a function, but I'm just choosing names that look a little more obvious. And here we're not going to apply f to x, we're just going to return x. With 1, we're going to apply it once to x. With 2, we're going to apply f to the result of f to the result of x. With 3, we're going to... So you see what's going on here is what we've done is we've defined our numbers as the application of a functional thing, an application of a lambda to something else. And the number of times we apply it repeatedly is the number. That is the thing. That is how we distinguish it. So 4 is equivalent to that. 5 and so on. I won't go innumerably infinite on you. There are a couple of observations. We could write it like that. There are some shorthands. In fact, to be consistent, we could write it like that. I'm not going to do that here. I want the full form. Also, I told you that lambdas, strictly speaking, only take one parameter, but it's a shorthand, and it's in the original paper, that you can basically go, oh, lambda fx, that's understood as being lambda f dot lambda x. And notationally, that's convenient. It just means that everything is curried. If you've done Haskell or looked at all this kind of stuff, all that's for free. That was built in. But I'm going to use this long form because it makes it a lot easier to turn this into JavaScript. Now, I know if those of you who work with JavaScript already know that JavaScript has a really weird idea of numbers. So we're not missing anything by skipping it. So here we go. I'm going to have _0. And the thing that's nice about JavaScript's choice of notation is it's actually one of the lightest. I've done this in a number of languages because I have a certain masochistic streak. And honestly, JavaScript is one of the easiest to do this in. It's syntactically light, and you can really see when you've gone wrong. But yeah, so basically, we've now recreated the number system. Awesome. But how do we know that it works? Well, what is that? This is a thing that does stuff. We are actually defining numbers by, or as it were, application. This is a thing that doesn't apply a thing. What's it not going to apply? Well, I'm going to plug in some good old-fashioned JavaScript. I'm going to take an increment. You receive an argument n, you add 1 to it, and that's your result. So we're not going to apply that because it's 0. And what is it that we're not going to apply it to? Well, I'm going to use the original 0 in the language. So we're not going to do that. And what's the result of doing this? 0. It's a JavaScript 0. What happens when we do it once? 1 applies f, n becomes n plus 1 once, which gives us that. And then we see. So in other words, the numbers, this is called a church encoding. These are church numerals, which if you read that out of context, it makes you think, am I talking Roman Catholics here? What are we on here? Church numerals. So these are church numerals. This is a really cool idea. It's moderately insane. Curiously enough, one of the best explanations of it I came across was in Shadows of the Mind, Emperor's New Mind by Roger Penrose, which is a book about why it is that we will ever create consciousness and a bunch of quantum mechanics and stuff. But, and ultimately you tend to think he has a great mind, but he's gone wrong. But it has one of the best explanations of this, and I think this is one of the first places I encountered it. It's just like, oh, okay, so numbers can be considered to be the act of applying something a repeated number of times. That's really cool. Okay, let's go back to our friend Square. So here's a really simple way of implementing it. We take a thing. If 2 is the 2-ness of something, I'm going to take m and I'm going to apply it to m. So that's squared. I'm going to apply m to m. How many times? Well, it's twice, isn't it? I'm going to do that. What happens if I put 7 in? Well, 7 is a thing that's a counting thing. So I'm going to apply 7 times. And 7 does 7 things. So, this is really cool, because we can now apply this straight. Start with 0. And the answer you've been waiting for since the opening minutes of this talk, yes, it is 49. Okay? But we've just recreated numbers. Now, why stop there? Why stop there? 19th century. Let's go back to the 19th century when we thought we could solve and know. Everything was knowable. Everything was logical. Victorian engineering had reached its peak. It's like, yes, the world can be understood through engineering, through maths. Everything will be understood. And the optimism is apparent in this gentleman's book title. These days, people just refer to it as the laws of thought, but clearly this is Victorian era. People are still into long book titles. An investigation of the laws of thought, which are found in the mathematical, etc., etc. This beautiful optimism that actually we think logically. Come the late 20th century, that edifice was torn down hugely. It turns out that logic is a thing that you learn. We are a mess. Logic is a tidiness that can only be acquired through education. But our default state is to be messy and irrational. I refer you to the activities outside this evening. So what did he do for us? Well, he basically formalized propositional calculus. And we live in a post-truth era, so I thought I'd just show you this, just so before you lose sight of what it is. And false. You know what? You can church encode this. I can apply, so lambda AB, truth is A, falsehood is B. So I've now got, oh, true and false. That's pretty cool. If you look carefully, although I've used different names, you may recognize this. If I did this as F and X, you may recognize this as 0. So for all those of you who've wondered, is false 0, is that just a programmer thing? No, it's actually built into the foundations of Lambda calculus that 0 is false. So next time you have one of those debates, depending on where you stand on it, but if you ever need to justify your gratuitous abuse of a language feature, and this happens to have been what you've done, you have a justification for it. Just refer them to the paper, they'll never get through it. Yeah, it's our friend Smalltalk. And what did Smalltalk do? Well, this is the whole thing. Smalltalk's idea of what is truth and falsehood is not there is a symbol called true and there is a symbol called false. Truth and falsehood do different things. So truth does one thing. This is polymorphic. If I give A and B to a thing that is true, I will get A back. I'll get the A part. So I've basically created a basic if-else here, which is kind of neat. So we can take this a bit further. It turns out you can get really carried away with this. Pair was originally introduced. So pair is you take an X and a Y and then you bind them together with an F and you kind of glue that together. You can pass it around. You can pass it around to an operation first, which will return you the X, or an operation second, which will return you the Y. And if you look very closely at those, you realize that first is basically pair of true, second is pair of false. This is quite nice. All you need to do now is add nil, and you've just reinvented Lisp. So it's just a ridiculously powerful formula. I'm not suggesting that you're going to go out and just just say, look, don't worry about it. The optimizer will take care of it. I am not going to use these mere mortal numbers and integers that you've been talking about using that domain-driven design thing of yours. We are going to build things from the purest of the pure. You know, oh, you mean you're going to use zeros and ones? Zeros and ones, dude, we're going to use lambdas. We're going to make our own zeros and ones. This is the craftsmanship movement. We make our own zeros and ones, finely crafted. So I'm going to end with an exploration of one of the most teasing challenges, FizzBuzz. What was interesting is a number of years ago, I guess it was about 10 years ago, I was reading a piece by Tom Stewart. It was called Programming with Nothing, and I suddenly realized I know what you're doing. It was a Ruby piece. And Tom solved it like this. Now, this is not a language you're familiar with, and I just said Ruby. Well, what did he do? Well, what he did is he basically programmed with nothing. He had those three properties. I can have a name of a thing, a variable. I can have lambdas, and I can apply a lambda. That is it. And he built up. And these are all the abbreviations. So he built up all of these concepts. He built the numbers 3, 5, 15, 100. He built logic. He built iteration. He did the whole thing. And you can find that on the blog, Programming with Nothing, but he also included it in his book, Understanding Computation. He also included the full form. If you expand it from the abbreviations, that's what it looks like. You know, it is one of the crazier versions of FizzBuzz I have ever encountered.
Big whiteboard.
Yeah, this is it. You know, this is the kind of stuff you give to somebody. Could you just work this one out for me? You know, I need some more detail here, yeah? Good luck debugging that, by the way. So, what we've found is this idea of lambda. It was, in one sense, a mathematical curiosity. It helped solve a problem. It was shown, and it was to do with the fact that it was such a simple formalism that even numbers could be encoded in it. And it had rules of reduction. And therefore, you had very simple operations. It turns out integers on their own are surprisingly hard. We tend to think of them as quite easy. But there's a whole load of stuff there. It's the idea of, like, I want to understand certain sequences. If I can encode everything in the simplest form, then I can provide proofs about it. And this turned out to be incredibly convenient. But this idea of an abstraction that was not about things, but about doing, if you like. It's about functions. That's not the usual candidate for this stuff. We normally, maths was always phrased in terms of objects, of things, not objects in the OO sense, but of things, of entities. Here we are talking about something that is much more intangible, a much more first-class idea of function. Rather than function being a convenience, it was actually a thing. And we can reduce everything down to that, so there is nothing else. And this proved to be surprisingly powerful. So powerful, in fact, that when people started thinking about, well, how do you build up simple languages? How do we do this? This idea of freestanding functions, whether we take it at its rawest level or start saying, you know, if only I could just pass a piece of doing stuffness around rather than having to name everything. If only I could just create everything and just pass it around. And we discover that that's actually been infused in a number of different paradigms. Obviously, there is a natural home in functional programming for this, but what we see is that it's not restricted to that every paradigm has ultimately ended up claiming it as its own because of that convenience. So I hope that has been thought-provoking and that you managed to stay awake. And that it's provoked some thoughts in you. Maybe you're just going to go home and drink that away, or maybe you're going to go home and say, right, okay, let's just try this. Oh, I can do this. Let's try a little bit of church encoding. COBOL, yeah. But, yeah, good luck with that. Thank you very much.